All right. Trig substitution. Continuing on. Let's think about this carefully together. Okay. Just by way of review. First of all, these are the forms of square roots that we're trying to kind of get rid of, right? And the way that we do that is we turn these sums and differences into a perfect square. And how do we do it? Well, we substitute in for the variable some kind of trig function. And then the Pythagorean identities allow us to turn that sum or difference into a perfect square. We replace it with a perfect square and the radical goes away, yes? And then we sort of keep track of what the price is we pay for that trig substitution. There's like a du or a dx or whatever to be dealt with. Then that hopefully will turn it into something that we know how to deal with. It's going to be a trig integral, yes? Which we know well and love at this point, hopefully. And we'll be able to do that trig integral. But one thing we have to remind ourselves of is that once we finish doing that trig integral, we have to do what? What do we have to do? We just leave it? We have to go back. We have to go back to the original variable. Sometimes that will involve a little bit of cleverness, you know, like using the double angle formula like we did last time. Remember that? We have to figure out like what cosine t and sine of t are equal to in terms of the original variable. A lot of times one of those two will be obvious and the other one, you know, will basically be the whole reason we made the substitution in the first place. It's going to be equal to like what the perfect square is, for instance. That is oftentimes what will end up happening, okay? So the goal today is to just continue to familiarize ourselves with these sorts of problems. Now, one thing I want to caution you against is trying to like memorize too many things. Like, okay, if I see this, I do this. If I see this, I do that. If I see this, I do that. Just kind of be flexible. You know, hey, we're just doing math, right? We're just having fun, trying to keep things loose, keep it light, right? And we're just sort of trying to feel, hey, what is it that I need to put in here to make this thing work, right? Don't try to like memorize hard and fast rules. I've just learned from experience that then I just end up with people in my office going, oh man, I can't remember all this stuff. And then I just think, look, just think about the Pythagorean identities and what you should do should kind of drive you toward the right process, okay? But let's do some examples here. Well, first of all, I just wanted to remind you that all of the trig substitutions we make are simply built on the back of two trig identities. Really, just the Pythagorean identity involving sine and cosine, and the Pythagorean identity involving secant and tangent. The third one is just a rearrangement of the second, correct? One thing I would point out is what did we kind of multiply each of these things by? You remember? Yeah, right. So we kind of multiplied this thing, right? We multiplied everything by a. And when you do that, you end up with like a squared cosine squared of theta. I like to use t just because, you know, then we're not, I mean, seriously, who wants to use Greek letters if you don't have to, right? So a squared cosine squared of theta is equal to a squared minus, and I'll write this all in parentheses, a sine theta quantity squared. And then like, you know, if this guy was equal to a squared minus, if I wanted this to be a squared minus u squared, then it's apparent that u would have to be equal to a sine of theta, yes? That would be the substitution you would make. Du would be a cosine of theta d theta, and we would be off to the races, yeah? Okay, any questions on that before we move on to some examples Any questions on that? All right, well, what I wanted to do was, let's see here. I'm going to do, well, how about this? Okay, I don't know why. Oh, yes, here we go. Yes. Okay, let's do an example here that involves something that we already know the answer to. Okay, so what about this? What if I had the integral of 1 over the square root of 1 minus x squared dx? Don't we already know the answer to that? We do. What is it? That is arcsine. Straight up. That's arcsine of x plus a constant, right? But let's suppose, okay, so let me just say, but suppose we forgot that. We forgot this. Okay? Well, then I might say, oh man, I have to do a trig substitution, right? Kind of have to like do a trig substitution. So what would I do in this case to actually do this trig substitution? Help me out here. And by the way, I think it's good. I mean, eventually we're going to get to where I'm going to have you guys working on your own at your desk. Yeah, try to bring your whiteboards, as much as possible, so that we can work on things together at tables or on your own. Collaborative math is the best kind of math. Okay, so what would be the sort of substitution that we would make in this case? Yes, sir. Okay, x equals cosine, or actually, okay, yeah. That would work, but one of them is a little bit easier, like x equal to sine, right? So because, you say, 1 minus x squared, I'm going to make that 1 minus sine squared of t, which, by the way, 1 minus sine squared of t is cosine squared of t, which is beautiful. And that means that I want x to be, what would x have to be? Sine of t, which means that dx is cosine of t dt. Know what I'm saying? Yeah? Okay. Well, look what's going to happen here. Like, what is the square root? So think about it. What is the square root of 1 minus x squared going to be equal to in this case? Square root of 1 minus x squared is the square root of cos squared, which is just cosine t. Look what's going to happen here. This is crazy. Okay, this is going to be the integral of 1 over, okay, that square root thing just becomes cosine of t. And what's dx? Cosine t dt. And you say, oh man, how lucky are we? The cosines cancel, and you're left with the integral of 1 dt. And you say, oh man, what is the antiderivative of 1 dt? Remember, you have to keep track of the variables very carefully. Writing dt and d whatever is very important at this juncture. It tells you what the variable of integration is. So what is this? What is this? What's the antiderivative of 1 dt? T. And then, of course, I go plus a constant. And I say, okay, how do I convert this back? So we need to convert back to x. Okay. So that means up here, I need to think about what the relationship is between t and x. Well, it's not too hard to do. If x is equal to sine t, what's t equal to? Yeah, t is equal to arcsine of x. So t is equal to arcsine of x. So coming back here, this is equal to arcsine of x plus a constant. And then all of a sudden you remember, oh, that's right. The antiderivative of that thing was arcsine of x. I forgot. But we just sort of figured it out again. Do you see what I'm saying? So the trig substitution idea is kind of telling us what the answer is to that antiderivative again. And also what the derivative of arcsine has to be. Yeah? So that's interesting. Okay? Any questions on that? Questions?
Okay, real quick. So if we had done it with the cosine, it would have gotten to something like negative arc cosine, and then that's just arcsine, right?
Yeah, that's right. Yeah. Basically, arc cosine has the same derivative as arc sine, but with a minus sign attached. Yeah. So you would have gotten that, yes. That's exactly right. Okay, other questions? Okay, let's do another one. Here we go. And this one I want you to work on your own for a minute, okay? Or with someone next to you. I want you to I want to turn you loose here, okay? So check this one out. Integral of the square root. Okay, remember, the thing you should always concentrate on is getting rid of the nasty square root, okay? Square root, and this is going to be a little bit different. 4x squared plus 9, okay? All over x to the 4th dx. And I am going to give you a while to think about this, like 10 minutes or something, okay? I want you to think about it for 10 minutes. What time is it right now? 11:15. So at like 11:25, I'm going to start asking for some input here. But I'm going to let you think about this, talk to people around you. I'm going to pause the recording even. Okay, so here we go. Okay, so start working. Let's talk about this. Okay, so once again, kind of getting started is the key most of the time. Okay, sometimes things can get a little dicey at the end when you're trying to convert back, but most of the time, I feel like getting started is the key, and then stuff will start to roll forward from there. Okay, so all of our concentration should be on the square root at the beginning, yes? Like what on earth are we going to do with that square root? Yeah. And in particular, we want to think about this, like the 4x squared plus 9, right? Which maybe I should write that as, I don't know, 2x quantity squared plus 3 squared, yes? Okay. And if I have a sum of two squares, which identity is it that I'm going to want to use? Or sum of two squares with one number and one like a variable, I want to use which one? Yep. Tangent squared plus 1 equals secant squared, but it's going to be a modified version of that, right? Okay. Basically, what we want to have is like 3 squared secant squared of t is equal to, I'm writing the perfect, or the sum of squares part on this side so you can see the comparison. 3 squared secant squared of t is equal to what? 3 squared tangent squared of t plus 3 squared, right? All I did was just multiply through the tangent squared plus 1 identity by 3 squared. You know what I'm saying? Okay. That's the same thing as 3 squared secant squared of t equals, how should I rewrite the 3 squared tangent squared t thing? How should I rewrite that? Yeah.
Where did the 2 go from the 2x squared?
It's still there. I mean, I haven't really tried to do anything yet. I'm just trying to rewrite the tangent squared plus 1 identity in a way that we can compare things. So how should I rewrite the 3 squared tangent squared t thing? Yeah.
I mean, could you write it as so you could write it as 2 squared times 3/2 squared and
Well, yeah, but I'm even like a couple steps behind you. So I'm writing this as just 3 tangent of t what? Squared plus 3 squared. You guys are way ahead of me. Okay, so then so then what? This guy right here, you want to compare with this guy right here, correct? So now say what you just said.
3/2 t quantity squared
Uh-huh.
times that's going to be times the 2 squared plus 3 squared.
Right. So those two things, like you know that 2x has to be the same as what? You're basically what you're saying is that 2x is the same as, what should 2x be equal to? 3 tangent t. Right, which is basically you're saying that x should be 3/2 tangent of t. Yes? We're just kind of making sure that things line up properly so that we think of the right substitution. So if x is equal to 3/2 tangent t, oh, and by the way, these guys are equal, right? The 2x squared plus 3 squared, like this guy right here and this guy right here are equal to each other, correct? So what does that tell us is true about 4x squared plus 9? Yeah, right? So another thing we know is that by design, 4x squared plus 9 is equal to 3 squared secant squared of t. Right? And therefore, if I wanted to take the square root of that thing, the square root of 4x squared, I mean, look, this is just how I work on these problems. I'm not even doing the integral yet, you understand? I'm just horsing around with like some algebra. The square root of this thing is equal to what? 3 secant of t, okay? And I know that x is equal to this thing. All right, so I have x is equal to this. I have this square root thing is equal to that. I can take this guy and figure out what dx is. What's dx? 3/2 secant squared of t dt. And I think now we're ready, right? So I think everything that we need. We have x. We have the square root of 4x squared plus 9, yes.
From the 2x equals 3 tangent t, what are we trying to get to after that?
Well, you know, you realize that you were trying to make 4x squared plus 9 equal something nice. But I still have other things I have to be concerned with. I have to figure out what dx is, right? Because there's a dx right here in the, right? I need to figure out what dx is. I need to figure out what this guy is equal to, yes. So that was part of what I was doing. But I also know that I have some other things in here to be concerned with. I need to replace x to the 4th with something. Does that make sense? So I really need to know specifically what x is equal to, right? It's not enough to just know what 2x is equal to. I need to know what x is equal to. So I'm just trying to collect all of the pieces of information that I need in order to replace the integrand with all the stuff in terms of the t stuff. Yes? Okay, so let's proceed. So help me out here. What's the square root of 4x squared plus 9 equal? 3 secant of t. Okay, over. What's x to the 4th?
That would be
Yeah, that to the 4th. Yeah. I don't know what's going on with 3 to the 4th over 2 to the 4th. Let's just leave it as 3 to the 4th over 2 to the 4th. Does that make sense? Yeah? So it's going to be 3/2 to the 4th. And how many tangents do I have? Tangent to the 4th of t. That's what x to the 4th is. X is equal to 3/2 tangent t. So when I raise it to the 4th, that's what I get. Yes? What am I still missing? And what's dx? 3/2 secant squared of t dt. Now let me ask you a question. Can I cancel some stuff? What can I cancel?
You can cancel a lot. You can just cancel all the coefficients and move them out in front of the
Sure.
integral.
So I can cancel an entire 3/2, correct?
Mhm.
So there are 3 of those left. Okay.
Cancel that top 3 with
Yeah, I can cancel the top 3 with another 3. Okay. And what I'm going to end up with is how many 2's? I could invert the 2's. How many 2's do I have? 3. So it's going to be 2 cubed. And how many 3's do I have left after the cancellation? 2. I'm just carefully tracking things. And now it's going to be the integral of what? Secant cube t. Secant cube t over tangent to the 4th of t dt. And you say to yourself, uh-oh, I don't remember doing a trig integral where I had junk in denominators and whatnot. But there was one recommendation that was made back in section 3 that we sometimes didn't take advantage of. What was it? Just convert to sines and cosines. So what is this going to be equal to in terms of sines and cosines? Right, so secant cubed, that's like 1 over cosine cubed of t. And the tangent to the 4th, I basically can flip that, right? The tangent sine over cosine. So you think of it as cosine over sine. So this is going to be cosine to the 4th of t over sine to the 4th of t dt. Okay. How many cosines cancel? Like almost all of them do, right? Like this can't, all of these cancel, and there's just a single cosine left, which is real good news for us. I'm telling you it's good news. Okay? Let's go to the, so hang on, I'm going to stop right there. Any questions so far? We've been doing some trig joscillations here. But do we have any questions so far? Any questions? Okay, before we move on to the next slide, okay, so we have, what is that, like 8, 9? Okay, so 2 cubed over 3 squared, that's like 8/9, isn't it? Yeah. So we'll just keep 8/9 in our mind. But do you see how you're going to be able to do this integral now? I mean, look, is there a substitution I can make? We've already made one substitution. Is there another substitution I can make? Yeah, set u equal to sine of t. And actually the top is cosine t dt. Yes, which is what the derivative of sine is. But I'm going to go ahead and write that on the other side. Okay, so next on the other slide. Okay, so just to remind us, we had the integral, the square root of 4x squared plus 9 over x to the 4th dx. We had made a substitution and we ended up with 8/9, the integral of sine t over cosine, or hang on, was it the other way around?
cosine over sine.
Yeah, sorry. Okay. Cosine of t. And I'll just to make it totally obvious, I'll write this as sine of t to the 4th dt. And we're going to put u equal to what? U is sine of t. Du is cosine of t dt, which is really nice. Okay. And so this is going to be 8/9, the integral of, yeah, u to the -4 du. And what is the antiderivative of u to the negative 4. Yeah, negative 1/3 u to the negative 3, exactly right. Negative 1/3 u to the minus 3. We have to add 1 to the power to do the antiderivative. And you have to divide by that power since it would come down in the antiderivative. So this is going to be 8/9 times negative 1/3 u to the minus 3 plus a constant, which, by the way, is just negative 8 over 27. Okay? Let me just extend this line out here and write this as u cubed plus a constant. And now we're getting close to the end here. Okay, so this is negative 8 over 27. Okay, what's u again? Right, so this is going to be sine cubed of t. Okay, sine cubed of t plus a constant. Now, we have to think to ourselves, we still want to go back to x. Do you know what I'm saying? We still want to go back to x, so we need to convert. How do we convert to x? How do we convert back to x? Remember, what was x equal to? X was equal to 3/2 tangent t. Yeah? So in other words, tangent t, what was tangent t equal to? x over 3/2, yes. I could write that as 2x over 3 also, right? Yeah? Does that make sense? But I don't want tangent. What do I want? I want the sine function, yes? I have sine cubed sitting there. What do we do?
Make a triangle.
Ah, watch this. Remember, what is tangent? Remember SOHCAHTOA? Remember SOHCAHTOA? What is tangent? A tangent of whatever. What is that equal to in terms of right triangles? Opposite over adjacent. Exactly right. So look, what's the opposite side length of, so I'm going to call this angle right here T. What's the opposite side length? 2x. What is the adjacent side length? 3. And what is the hypotenuse length of this triangle? Hey, what does that remind you of? The square root of 2x quantity squared, right? Because because the square of the legs summed together has to equal the square of the hypotenuse. You have to take the square root of the sum of squares. What do you end up with? The square root of what? Ah, does that seem familiar to you? Wasn't that the thing that we started with in the numerator? It's sitting right there. Do you see that up there? Okay. But now I have this triangle. By the way, this guy is often referred to as a reference triangle. It's often referred to as a reference triangle. So what is sine of t? Right, so that's opposite over hypotenuse, is it not? Right, because SOHCAHTOA. So sine of t, using this little reference triangle, is opposite over hypotenuse. So it's going to be 2x over the square root, right? 2x over the square root of 4x squared plus 9. Okay? So we were able to sort out what sine t was from that little reference triangle. Yeah? So what's the answer going to be here? What do you think? Going back into our thing right here, it's going to be negative 8 over 27. What? You put what sine of t is in here, which, right, it's negative 8 over 27. What's sine of t equal to? 2x over the square root, oops, the square root of 4x squared plus 9. And what do we have to do with that junk? Cube it. Hey, something interesting is going to happen here. And by the way, this is plus c. Something interesting is going to happen here. What happens to the 2 and the, like, see, there's going to be a 2 cubed. And what happens to that with that in terms of the 8? Yeah, this and this actually cancel completely. Right? You have a 2 cubed down here that cancels completely with that thing. So look, and I could actually flip some stuff. Look, I have the square root of 4x squared plus 9 raised to the 3rd power. But what's the square root? If I wrote that as a power, what would that be? 3/2, right? Because square root's 1/2, raised to the 3rd power, it's like 3/2. Okay? So let me, and I could flip that upstairs. And look at this. This is going to be negative 4x squared plus 9 to the 3/2 to the 3/2. And what's going to be downstairs? Over 27, what? What was that? Yeah, 27x cubed plus a constant. Yeah? Amazing. There it is, right there. Right there in all of its glory. Okay? Now you might say to yourself, holy mackerel, how can I be confident that I didn't make some kind of mistake in the process? Like, we had lots of constants we were trying to keep track of, yes. Right? This is sort of a lengthy problem. One of the issues is we ended up with a trig function that time that wasn't part of the substitution process. Do you know what I'm saying? In the substitution process, what trig functions were we monkeying around with? Secant and tangent, yes? And in the answer, we ended up with sine. So what did we have to do to kind of go back? We had to make a reference triangle, okay? That's like a little, so that's a further step of complication, but it's kind of nice. You have this little geometric piece that helps you think through what's happening in terms of how these are relating to one another. But what could I always do to kind of check myself to make sure? You can take the derivative. Yes, there was a hand up right here. Yes.
If my initial thought, instead of making a reference triangle, was to do like the inverse tangent of x over 3.
Yeah.
Would that be right, or would you have to?
Well, that would be a way to write the answer, but that, I mean, that'd be pretty gnarly, right? You would have sine of, and what would be inside of the sine function? The inverse, the arctangent function of what, 2x over 3 or something like that, right? That would technically be a right answer, but I would contend that this is probably a little bit nicer because it at least doesn't have any inverse trig functions in it. Does that make sense? What you just said is equivalent to this answer. Okay? Other questions? I think that's pretty cool. I don't know. I know it's complicated and it feels sort of weird and unusual, but this is the first time you've seen one at this level of depth before, okay? Most of them certainly aren't going to be as in depth as this one perhaps, but what I want to do now is I actually want to check this answer, okay? So we have, you guys, so I want to check this answer, but I don't want to go through the rigmarole of actually computing the derivative by hand, okay? So let's go ahead and do that. I'm going to share my screen here. Okay. Okay, you guys see it? All right, let's see. Let's go in and open up a tab here. Let's go to like Wolfram Alpha or something. Okay. Okay, what am I going to do? I want to take the derivative. So I always go like this when I take derivatives. I go d something dx. What am I going to put in here? It was like negative something. It was negative, what was it? 4x squared plus 9 raised to which power? Oh boy. 3/2 divided by, okay, I'm going to have to put this in parentheses down here, 27x cubed. If I wanted to be really cute, I could write that as like 3x all raised to the third power or something like that. You know what I'm saying? Let's just leave it at that. And I want to take the derivative of this thing. And in theory, what should spit out is the answer. Hey, is that it? Square root of 4x squared plus 9 all over x to the fourth. It is, right? So we know that we're in business and that we handled this thing rightly, okay? All right, any questions on that? Questions? I'm gonna go back in here, kind of talk through some stuff. We already kind of did this one. If you use a trig sub with recognizable arc trig problems, we already did this, right? We did it for the 1 over the square root of 1 minus x squared. And we pretended like we forgot. We had kind of had a brain lapse and forgot that that was just arc sine of x. But did we still get to the arc sine of x eventually? Yes, we did. And that's precisely what would happen if you made a substitution in this particular case. What would be your substitution in this case, by the way? Just to kind of keep us on task here, what would be the substitution in this particular case? What would you put u equal to? U equal, yeah, well, u would be a sine of t, because then a squared minus u squared would be a squared minus a squared sine squared of t, yes? Which would be what? A squared cosine squared of t. And what would du be? A cosine of t dt. Does that make sense? And then so what would the square root of a squared minus u squared be? The square root of a squared minus u squared would end up being a cosine of t. You see it? Yes? Interesting. Okay, so this whole integral, what would this turn into? 1 over, I would have the square root, it would be 1 over this square root, yes? So it would be 1 over, what is that thing? A cosine t. And then what's du? A cosine t dt. And you say to yourself, what in the world? What just happened? Those canceled. So what do we end up with? The integral of 1 dt. And therefore, what's the answer to this thing? T plus a constant. And now what's t? I ask you. Okay, well, that's going to come from this guy over here. Okay? Think about it. U is equal to a sine of t. So what's sine of t equal to? Sine of t is equal to u over a. So what's t? Arc sine of u over a. So what does this antiderivative end up being in the end? Arc sine, I'm running out of room here. U over a plus a constant. Sorry guys, I'm out of room, but it's on the next page anyways, okay? So do you guys see that we could have done the exact same thing we did in the case of the square root of 1 minus x squared, okay? So on the next page here, look, all of these, we can kind of rediscover all of these little formulas. I don't want you to necessarily remember all of these formulas, but these formulas right here just automatically come from making the appropriate substitution, just the standard square roots, okay? But again, on the previous slide, we discovered, here, let me actually go back one and rewrite this. We found out that this was indeed equal to what? Arc sine of u over a plus a constant, yes? Okay, but in general, there are lots of other things that you could kind of do that are far more, that end up with answers that are far more complicated that you should never memorize, right? But these things, this is the general form that you would get, okay? Any questions on that? Questions on that? Okay, well, let's do another problem. Actually, let's do that. Yes, let's do this. How about this? Here we go. All right. How about this? What would you do with the antiderivative of x times the arcsine of x dx? What would you do? X times the arcsine of x. Yeah. Let's try integration by parts. Remember ILATE. That's what's going to get priority as being put equal to u as you read left to right. So what would we put u equal to in this case? U, of course, would be arcsine of x, because who on earth would be insane enough to find the antiderivative of arcsine of x just off the top of their head, right? So u is arcsine of x. dv, what's dv? X. du, okay, what's du? Yes. And what is v? What is the antiderivative of x? 1/2 x squared. Yes. Okay, so this guy, you go u times v, which is 1/2 x squared arcsine of x, minus the integral of v du, right? So minus 1/2 the integral of x squared over the square root of 1 minus x squared dx. And you say, oh man, that's maybe a little bit better, but I have that nasty square root in the denominator. But now you have a new tool in your toolbox. What could we do to handle that remaining integral? What do you guys think? Trig substitution. What would you do? Think about it. What x would be what? Sine of t. Okay. So the suggestion is to make x equal to sine of t, because then what's 1 minus x squared? Well, that would be 1 minus sine squared, which is, what's 1 minus sine squared? Cosine squared of t. And what is dx? Cosine of t dt. Very good. I think we have everything we need, except maybe we should just observe that the square root of 1 minus x squared is equal to just what? Cosine of t. Okay, going back over here. So this is 1/2 x squared arcsine of x minus 1/2 the integral of, okay, this is going to get interesting, x squared. What's x squared? Sine squared of t. And what is, okay, what is the square root of 1 minus x squared? That's just cosine of t. Okay, and what is dx? Cosine of t dt, of course. And of course, the cosines cancel, which is really nice. What's going to happen with the integral now? The integral now is just the integral of sine squared of t. I'm trying to remind you of things that we've been doing in recent days, right? Isn't this amazing? Think about it. We just did integration by parts. Now we're applying trig substitution. Now we have a trig integral, and now I'm forcing you to remember which formula? Half angle. Remember what the half angle formula is? Yeah, sine squared t is equal to 1/2 what? 1 minus cosine of 2t. Yeah? Okay. So moving on. Writing this out, this is 1/2 x squared arc sine of x minus, okay, if I replace sine squared with that junk, that 1/2 is now going to be a, what is that? A fourth? Okay. And it's going to be the integral of what? 1 minus cosine of 2t dt, right? 1 minus cosine of 2t. And now what do we do? Okay, well, let's just write this out. It's going to be 1/2 x squared arc sine of x minus a fourth. Okay, help me out here. Remember, this integral is in t now. What's the antiderivative of what? T? What is the antiderivative of cosine of 2t? Yeah, 1/2 sine of 2t. That's exactly right. Oh, man. Sine of, oh, man. Sine of 2t. Running out of room here at the end. Plus a constant. Okay, someone's going to have to read this off to me on the next slide. Okay, so remember, so let me just kind of take a brief glance at this, and we'll move over to the next one. Okay, the integral of x arc sine of x dx equals 1/2 x squared arc sine of x minus a fourth t minus a half sine of 2t. Did I get it? Okay. But what do we need to do here again? Yeah, so we need to convert to x. Okay, convert to x. All right. But what was, so help me out here. Remember, we had some stuff on the previous slide. Let me see here. We had some stuff on the previous slide. For instance, x was sine of t. X was sine of t. The square root of 1 minus x squared was cosine of t. Yes, I'm looking at this thing and at this thing right here. You see that? Yeah. So let's remember that. The square root of 1 minus x squared, that by design was cosine of t. And what was x? Sine of t. But I do not have sine of t. I have sine of 2t. What do we do? Double angle. Sine of 2t. Trying to give you a problem where literally everything we've been doing kind of is brought to bear. Yes? Listen to what we've done so far. Integration by parts. Remembering the derivative of the arc sine. We've had to do the trig substitution. Now what have we had to do? We had to do a trig integral where we had to use the half angle identity. Now we're doing the double angle identity, right? So everything is happening in this problem, which is awesome. Sine of 2t is 2 sine t cosine t, which, by the way, what's that? What is sine of t equal to? So that's 2 what? X, and what's cosine of t? Square root of 1 minus x squared. Right, so that's going to go right there. What's going to happen to the 2's? What's going to happen to the 2's? Yeah. This is going to be minus 1/4. Okay, let me ask you a question. What's t equal to? Yeah, that's just arc sine of x again. That's amazing. Arc sine of x, because x is sine of t. T is arc sine of x. The 1/2 and the 2 cancels, and what are we left with? Minus what? X times the square root of 1 minus x squared. Okay, plus a constant. There it is, my friends. It's pretty amazing. Now, I suggest that that be the last problem we do, but I do want to actually, I mean, we'll just stare at that for a minute. Look at that. That's amazing. Yeah, stare at that for a minute. That's an amazing answer. But it's hard to, at this juncture, it's kind of hard to trust that that's all there is. So I suggest that we do one more thing. What do you think I'm going to suggest we do? Yeah, so let's do that. Okay, so I'm going to go over here. Okay. I'm going to get out of this thing. Okay, and I am going to go and take the derivative. What was I taking the derivative of? Well, I'm going to copy this down. I have it right here with me. And it's going to be, oh wait, maybe I don't have it here with me. Can someone read it off to me? Yeah, so it's x squared times the arc sine of x. Yeah, over 2, okay? Minus something over 4. What is it? Something over 4. What was inside of here? So arc sine of x, beautiful. Minus what? X times the square root. I don't even know if this is going to work. Like I just typed square root in there thinking that it might know what that means. Is that what it is? It's 1/2 x squared arc sine of x minus 1/4 arc sine of x minus x square root of 1 minus x squared. So let's see what happens. Hey, there it is. X arc sine of x. There it is, except they like to use the sine inverse notation. There we go.
So quick question.
Yeah.
So back when we were doing the integration by parts, we did find a way to find the antiderivative of an arc sine. And given all those hoops we just jumped through, is there ever a condition where, given a problem like that one, where we got to like realize it was going to be a lie, would it ever just be faster to just find the antiderivative of an arc sine?
Antiderivative of an arc sine, I'm not, oh, there is, well, but I would suggest the antiderivative of arc sine was complicated enough, you would have still ended up having to do, so what you're saying is, what if I would have put dv equal to arc sine? We did find the antiderivative of arc sine at some point. I contend that you still would have ended up with something that would have required a trig substitution. You can go check that, like go back and actually use the notes, but I think you still would have had to do something. Perhaps. I could be wrong, but that's a good question. Okay? All right. That's it.